Hello again, everyone. We are back. Hopefully, we'll do better today than we did yesterday because yesterday did not go so well. I would love to say that I got more sleep and I'm ready and fresh for another puzzle, but I did not. So, yeah, we'll see how it goes. It's also absolutely freezing in here. I don't know what temperature it is in Edinburgh right now. It's like, it must be, it says -1. This room is like part of an extension, so it gets freezing cold. I've got like a electric radiator right next to me, so that should help. I did actually manage to go back and work out what the problem was with my code for yesterday. The problem was I misread the instructions. Basically, I was checking adjacent trees to see if one was visible, but you need to keep track of the maximum height when you're going down and across. So yeah, misread the instructions, got it wrong. So let's see if we can not do that this time. Okay, day 9, rope bridge. This rope bridge creaks as you walk along it. You aren't sure how old it is or whether it can even support your weight. It seems to support the elves just fine though. The bridge spans a gorge which was carved out by the massive river far below you. You watch carefully as you do the rope stretch and twist. You decide to distract yourself by modelling rope physics. Maybe you can even figure out where not to step. Consider a rope with a knot at each end. These knots mark the head and the tail of the rope. If the head moves far enough away from the tail is pulled towards the head. Due to nebulous reasoning involving Planck lengths, you should be able to model the positions of the knots on a two-dimensional grid. Not two-dimensional grids again, our nemesis from yesterday. But I'm going to read the instructions properly this time, that will help. Hey Gray, hey Stuhlpenner. Then, following a hypothetical series of motions, your puzzle input for the head, you can determine how the tail will move. Due to the aforementioned Planck lengths, the rope must be quite short. In fact, the head and the tail must always be touching, diagonally adjacent, and even overlapping. Both count as touching, okay? So that's horizontally adjacent or orthogonally adjacent, and this one's diagonally and this one's covering, okay? If the head is ever 2 steps directly up, down, left, or right from the tail must also move 1 step in the direction so it remains close enough. Okay, so if we're in this, so assume if the head moves in this position, like to the right, then the tail does nothing. But then when the head moves 1 additional space over, then the tail has to move. Okay. Otherwise, if the head and tail aren't touching and aren't in the same row or column, the tail always moves 1 step diagonally to keep up. Okay. So if it's here and it moves up, the tail both moves up and right. Okay. You just need to work out where the tail goes as the head follows a series of motions. Assume the head and the tail both start at the same position, overlapping. For example, right 4, up 4, left 3, so on and so forth. After each step, you'll need to update the positions of the tail if the step means the head is no longer adjacent to the tail. Visually, these motions occur as follows. Okay, let's just walk through this, because last time I did not walk through everything. I was like, I've got this, and we misread the instructions. So we start off covering. Head moves right 4. Okay, so in each step you have to update the position. Hey Vagrant. Okay, and then we move up 4, so it moves there. It's still touching, so tail doesn't move. Then it moves up again 1, so the tail does that diagonal movement, and then up, and then up, and then left 3. We do that diagonal movement again. Down 1, no movement, right 4, no tail movement there. Does that diagonal move and regular follow. Okay, I think we've got the hang of it. After simulating the rope, you can count up all of the positions the tail visited at least once. In this diagram, S again marks the starting position, which the tail also visited, and hash marks the other positions the tail visited. So there are 13 positions the tail visited at least once. Okay, so we're gonna keep track of everything. We could like actually keep a grid in memory, but I don't think we actually need to do that. I think we only need to keep track of the coordinates of head and tail. And every time we move, we adjust the position of tail and we add the coordinate of the tail to a set, and then at the end we return the length of that set. I think that should work. Alright, let's give it a shot. New day. Day 9. Almost in double digits now. Okay, so let's say that our positions are going to be coordinates. We're going to use... should we make these longs? I don't know how much movement we're going to be doing. So we're going to have a coordinate for the head and a coordinate for the tail. Then we're going to have a set of coordinates. If we do spaceship operator, I think we can default the spaceship operator to get comparison operations ourselves by default. I didn't want Wikipedia. I wanted CPP reference. Default comparisons. Okay, yeah, we can do this. And this will do a member-wise comparison of X and Y. Like, I could use a stood pair, but it's nicer like this, I think. Set of coordinates is going to be our positions visited. So we're going to do instructions as TL views get lines of our input, and we'll just stick it in a vector. Actually, we don't need to. Okay, so for each instruction, we're going to split it on. Well, we don't need to split it. Well, that depends. Are we ever moving more than 9 spaces? It doesn't look like it to me. Looks like... Oh, no, we are sometimes. Yeah. Okay, so we do need to do a split. Split into stood string, our instruction. So our direction is S0 and our amount is stood S2I of S1. Okay. So we're going to begin with these at 0 and 0. And it could go into the negative. And we'll do it in the same way as this. So 0, the origin represents the bottom left. So we're going to do is less than amount. Okay, so for each of these, we're going to do a move. Direction, head, tail, and this should give us a new position for the tail. It's going to have to update the position for the head as well. So let's just pass them in as references. So our direction, our head, our tail. Okay, so first we can let's just move the head first. So we can switch on direction. If it's right, then I'm just gonna open a window. I have a little CO2 monitor in here, and it's like, hey, open a window. So if we're right, then we're going to move our head.x. If we're left, if we're up, up is going that way, down. Okay, so that moves our head. Now we need to work out if we need to make a move with tail. So the possibilities were, if it's 2 steps directly up, down, left, or right, then the tail moves in that direction. If the tail is also 1 away on the other axis, then we move diagonally. So this is like, are these instructions slightly inaccurate? Because it's saying like, if it's 2 steps directly up. Okay, no, because this is saying directly up. Yeah. So we can make this check first. Like, so if the absolute value of head.x minus tail.x is greater than 1, or absolute value of head.y minus tail.y is greater than 1. So if we are at least 2 spaces away, then we're going to have to move. So then if we're additionally 1 away in the other direction, you know, let's split this up actually. Let's look at the y-axis. so the x-axis. So if the distance in the x-axis is greater than 1, then if the y-axis distance is also 1, i.e. we're not on the same column, then tail dot x is going to have to move in the same direction as head, which is going to be tail dot x plus 1 multiplied by whichever our direction modifier is, which is maths, and I hate maths. Basically, we can check the head.y minus the tail.y, and that will be positive or negative. We can make a function for this. So we're going to move our x position in the direction of head, and we're going to move our y position also in the direction of head. Otherwise, we're just going to move our x position, so we can just do this. Otherwise, if our y values are different, then we're going to do all of this stuff. We could abstract this out. Maybe I'll do that if we get it right. Okay, so Dermod is going to take along for the head and along for the tail, and if head is greater than tail, then we're going to return 1. Otherwise, we're going to return -1. Okay. So this is going to start off initialized to zero, 0, because we start off there, and then every time we do a move, we're going to positions visited dot insert our new tail position, and then at the end we're going to output the size number of positions we've visited, and we're going to need set, and could work, could break horribly. Let's find out. Let's get our instructions from here. Does anyone immediately see anything wrong with my logic? Whoops. space. Can't convert from. Oh, okay, this returns us a string, so we know it's only one character, so we can just get that single character. Okay, let's see what happens. 13, hey, that's the right answer, isn't it? 13, okay. Let's give this a shot. 6181. Yay! Oh, that feels good after yesterday. Let's make this a little bit prettier. We can factor this out. Make this a lambda. Check axis. Capturing head and tail by reference, and it takes axis 1, axis 2, and whoops, we're gonna do, instead of calling .x, we're going to do axis 1 of head. We're going to pass these in as functions. Axis 2 of tail. And then, what was that? That was x. Yes. I could no, that's wrong. I can very easily get all of this wrong. I could use a regex replace for this, but it's fine, I'll just write it out. Axis 1 of head, axis 1 of tail, and then y is going to be axis 2 of head, axis 2 of tail. Then this is axis 1. This just lets me avoid the duplication. So I do check axis with chord x and chord y. Don't you need axis on the left hand side as well? Yes, I do. Yeah, thanks. And then I do check axis the other way around. Chord y, chord x. But of course, if I'm passing member function pointers, I can't use regular call syntax. I need to do something slightly different, but let me just do, this was axis 2, right? And axis 1. So you can pass member function pointers like this, but then you can't call them with the regular call syntax. I could pass lambdas, but another option is to do, no, I will use regex replace for this. Axis with some digit, and then some name with bracket escapes. Oh, how does the assignment for the axis work? Oh, it doesn't, you're right. Or do member function pointers give you back an L value? I feel like they probably do. Pointer to member. You know, let's just get part 2 working, and if we get it working, then we can come back to this nonsense. But I should be able to abstract that out. Anyway, part 2. A rope snaps. Oh no. Suddenly the river is getting a lot closer than you remember. The bridge is still there, but some of the ropes that broke are now whipping towards you as you fall through the air. The ropes are moving too quickly to grab. You only have a few seconds to choose how to arch your body to avoid being hit. Fortunately, your simulation can be extended to support longer ropes. Rather than 2 knots, you must now simulate a rope consisting of 10 knots. 1 knot is still the head of the rope and moves according to the series of motions. Each knot further down the rope follows the knot in front of it, using the same rules as before. Jeez, okay. Using the same series of motions as the above example, but with the knots. Wow, this is... I don't like this. Now you need to keep track of the positions. The new tail 9 visits. The new tail 9, in this example, the tail never moves and so it only visits one position. However, be careful. More types of motion are possible than before, so you might want to visually compare your simulated rope to the one above. Okay, so what are some of the new types of motion that can occur? I guess it can, like, you do one movement with the head, and that results in you having to run an update multiple times because it has like a knock-on effect. So moving down. Okay. Whoa. This one looks a bit tricky. How many positions does the tail of the rope visit at least once? Okay, well, let's see. So, right now we just have a single head, and every time we move the head, then we move the tail. Now, it should be that calling move should never like make an update when it doesn't need to, right? So we don't really need to worry about that. We basically have, I'm just going to copy all of this for now. So instead of just a head and a tail, we're going to have a std array of 10 coordinates, which is going to be our knots. Incomplete type, I don't have a hash include array. Okay. And all of these should get default initialized to 0 because I have that. Oh, Marshmallow's coming to visit. Hey Marshmallow, can you come say hi to everyone on the stream? This room is a bit messy, so he's trying to get... Hey, come say hi. Up you come. He doesn't want to come visit. He's just like screaming randomly, but doesn't want to come up. Come on. Come say hi. Come say hi. No, he's just gonna chill in this room and maybe he'll come say hi at some point. Oh, okay. So we basically want to do, when we move, instead of doing just one move, we want to loop through all pairs of our knots. So we could do for auto, we can call this lead and follow. In TL views pairwise, can just take pairwise, which is in TL adjacent. Pairwise of our knots. Then we do move with lead and follow, and then at the end we do dot insert knots dot back. So now initial now, does this cover a situation where, like, the rope, where you have to get multiple movements in one move? Marshmallow, you're just knocking stuff off. Why don't we just run this and see what happens? Yeah, let's just give it a shot and see if, well, that's, I think, the same as we got for part 1, so very likely not the right answer. Yeah. Okay. So let's try this with the initial input. Marshmallow, what are you up to? Where's our initial input? All the way up here. Okay. Marshmallow does love to scream. It's his favorite pastime. 13 again. Whereas the actual answer should be like 1. Because it doesn't move. Okay. So that's, we've obviously made a mistake. So what are we doing? Do we need to write a visualizer for this? We'll step through it quickly and see if there's any, like... Oh, we don't even call part 2. Jeez-o. That's, yeah, that's not going to do anything, is it? If it's not calling the actual function. We're probably not going to get the right answer. Let's see what answer we do end up with. We did end up with 13 anyway, so. I did end up writing a visualizer for part 8 to solve my problem that I had. I'll quickly show you it, because it's kind of nice, actually. I use ANSI color escape sequences. Oops. Day 8. yeah, so I wanted to visualize which trees were visible. So I made it output all of the trees, and if it was marked as visible, then mark them red. So this could show me like if I was doing it wrong or not. You can see it's right, like 0, 1, 3, but then none of these are visible. Then 4 is 5, basically like all of the climbing up numbers. Kind of cool. I like it. Dr. Demon saying this reminded me why I do it in Python every year. Yeah. Okay, so where were we? Let's quickly just step through this. See if we notice any mistakes, and if it's not obvious, then we'll write a visualizer for it. So we start off, and our knots should all be 0. Yeah, that's an obvious mistake, is that I'm like explicitly moving every single knot apart from the last one by giving it this dir. So what I really want to do is split this up into a move and an update. So the head gets moved, but then we just do an update to update the relative positions. Move, update. Okay, so we move knots 0, and then for all of the other ones we just do an update. Alright, so at this stage our head should have moved, and then we're going to do a bunch of updates. Our first move shouldn't move anything because head has not moved far enough. Yeah, there we go. Okay, so then we get back and we move head again. Whoops, let's just continue to there and then set this back. Okay, so our knots are head moved and nothing else moved. That's correct. And then our head moves again, so number 1 should move and the others should not. Yeah, that looks good. So let's see where our knots end up at the end. Our position visited is 1, so that is the right answer. Let's have a look at... yeah, I am kind of abusing in-out-ref parameters. It's not nice, and I do apologize. So our state is 2 up, 2 across. That doesn't look... Oh, right, yeah, head is there. So that's correct. Whoops. So head is correct, 1 is correct, H covers 2, which is correct, and 4, yes. 3 is to the right of it, yep. This one is 1 down. That's not correct, is it? This one should be at 1, -1. Yeah, I think this one is wrong. No, why is that? Alright, I guess we'll write a visualizer. Alright, what are my bounds here? I've got 1, 2, 3, 4, 5, 6. 6 by 6, so we can visualize on a 6 by 6 graph. So after every... how much does this graph update? This is doing it every iteration, so here. Output state of our knots. Okay. And we'll make it 6 by 6. Output state is going to take our knots, is going to take X and Y sizes. Okay, so for I0 is less than Y plus I. If okay, so how are we going to visualize this? Because we want to show the topmost one. So we're going to do a find if topmost equals thanks to follow J. Lewis views find. So we're going to find in knots the coordinate x, y. I think I'm I might end up like transposing this or something. We can add some negatives in there if it gets wrong. So if topmost is not knots.end. So if we did find, if there is a knot there, then we're gonna output the index of our knot, which is the distance from knots.begin up until topmost. Otherwise, we're going to output a dot. And then at the end of each iteration, we're going to output a new line. Oops. Okay, and then once we've finished, let's output a couple of new lines just to visually separate everything out. Alright, so this should output the state at every step. Oh, it's not instant views.find, it's instant ranges.find. Alright, let's see what we get. That's not quite what I had in mind. I don't know what's going on here. Let's stick a breakpoint here. Anyone see what's wrong in my output code? So we want to find 0, 0 in our knots. Which should return 1, but topmost is end. Why? God damn it. I was checking X and Y instead of I and J. Not the best move. Okay, so it's transposed, and I don't know what this is, but apart from that, where does that number come from? Isn't that just the puzzle input? Oh, single quotes are in this. Yes, thank you. Alright, let's try this again. Marshmallow, you don't have to scream. You can just come and say hi. I don't know if you can hear him on the stream, but he's just sitting there like screaming to himself a bit, having some fun. So what I had before is called a is it a multi-byte character or something? I can't remember what it's for. How many days to learn C++? I mean, how long's a piece of string? It really depends. Okay, well, this is obviously incorrect. I'm not sure if it's... it's probably because we're going off the edge and I need to do a negation somewhere. Let's do... I think our y-axis is negated. Well, that was obviously wrong. Let's stick a breakpoint in here and work out what we're doing wrong. Marshmallow, come and say hi. Don't just scream at my door. Yes, Marshmallow has had today's thought. Marshmallow's thought every day is scream. That's all he thinks about. So this stage, what is not? So we keep going for a bit. Our y-axis is negated, so we're putting our right, it's j negative I. Axis orders. Okay, how does this look if I just continue? Okay, this is looking a little bit like it's doing something. It will be slightly different to this because it's the other way around. We can flip it if it becomes too difficult to parse visually. Okay, so that all looks correct. We get to this point and we're all good. Yep, we do that, we're all good. Yeah. Then this one. Ooh, look at that right there. That's wrong. That 5 should have moved. So we potentially need to, call update multiple times in case there's a chain reaction. You know what I'm gonna do just to see if I can get it working? I'm just gonna call update 10 times because it shouldn't make a difference if I call it and I don't have to. It's probably like there'll be a maximum to the number of times it can update. But you know what? Just to see if we can get this going, and then maybe we can think about a nicer solution later. I mean, that looks better, right? So we're in this position, and we it's still not quite right. See, we're here. Here at this point, and then 0 moves down, and this 6 is in the wrong place. In fact, the 5 is in the wrong place as well. Okay, so maybe there's a move here which we need to actually encode into our update if there's a larger distance between our knots. So here 4 moves such that it's in fact 2 spaces in both directions. Yeah, 4 moves there, and 5 should go diagonally. Okay, so that is something that we need to encode into our update function. So if both of these are true, so if we're different from with a size of 2 from both axes, then Marshmallow wants to visit again. Or you just want to scream? Oh, come say hi. Here's Marshmallow. He is baby. Do you have any thoughts you would like to share with the world? He's a very sweet boy. Just a teddy bear. Aren't you? He's half ragdoll, so he'll let you pick him up and just do anything, won't you? Yes. Okay, so in this situation where they're where we're two spaces diagonally, then we want to do both of these. Maybe that's caught by just removing that else, but I'm just gonna do it this way for now. Okay, let's try that again. See if we get the correct visualization. That might be the only thing which was wrong. So the problem occurred right here, and that's correct. That's what we were looking for. So then, how's our end state? Our end state is 10356. That's correct. Okay, cool. Let's try with the larger example, see how we end up. What is this? Yes, I'm just copy pasting this into character counter to give me, okay, 26. Is this a square? This is just so I can tune my visualizer. 21 by 26. I'll just make it a square and see how we go. Where is our input? Taking a little bit longer. Oh, that didn't look good. Well, I guess we flow off over. I guess we had a window that we were viewing, and we kind of flew off the end of it. Anyway, did we end up with the right answer? 36. That is what we got. So we could be... could be there. I'm gonna disable my visualizer. Otherwise this will take all day. And we probably don't need all of this because we handled that case when we're diagonally away by 2. 2386. Yay, we did it. Nice. Let's just make sure we get the right answer. Two, 3, 8, 6. Amazing. All right. There will be ways that we could clean up the update function, but you know what, for now I'm just gonna leave it. Is it enough to change these to greater than equal? Because then we move in that direction if this is 2 as well. 2, 3, 8, 6, yep. That does the same thing. So then we could abstract this out a bit, like, do we want to try and do the, we've been here an hour, I don't really want to do the whole member function stuff. This works, it's fine. Cool, yeah, I'm happy with that. Alright, thanks for joining everyone, and I will see you tomorrow.